Assalamu alaikum everyone. So this is the 8th lecture of the course, and today we're going to learn about a different kind of network entirely compared to the traditional network that we know of. So this network is called software defined networks, and we are going to learn slowly why specifically it's called a software defined network. So what is an SDN, or software defined network? So SDN architecture divides the traditional protocol stack into two separate planes or sub-planes. So the first plane is a data plane, which consists of switches, and this plane can only forward messages or relay messages. And the second subplane is the control plane, which consists of controllers. So these controllers are the decision makers. Okay, so the traditional protocol stack means specifically the network layer, and the data plane can only forward messages and cannot take any decision like where to send the message, or routing decisions, or even broader scale decisions, for example changing the routing table, or detecting failures and how to deal with failures. So the control plane takes all the decisions. When the data plane encounters a new packet, one which is not present in its routing table, or one regarding which the switch does not know where to send the packet, it always asks the controller and queries the controller about where to send, and the controller takes the decision and lets the data plane know. So this is an example of a traditional network switch compared to a software defined network. So as you can see here, this is a switch, a traditional network switch, and as you can see, the control plane and the data plane is together. So what does it mean? This means that a switch or a router takes a decision of the routing, and deals with link failures and what decision to take using the control plane of that switch, and the data plane forwards that message accordingly. So both functionalities are contained in a switch, which is why they are sometimes also called intelligent router nowadays, because they have many other functionalities. Compared to that, in case of a software defined network, the switches are programmable. That means they cannot take decisions, but they can be told what to do. And instead of the control plane being present in the switches, it's a separate entity now, which is called a controller, or in this case it's a controller machine, and this controller is connected to all the switches, and the controller lets the switches know what to do. So in case of traditional protocol stack switch, the data plane and the control plane is together, right? So the control plane contains all these things. So it has the build information, that means the ARP, address resolution protocol, and the different protocols, different routing protocols, and all these things are present in the switch. That means they know the different protocols, and they also store information. For example, they have the forwarding tables in the different caches present in the switch, and they can also take their own forwarding decision based on this information, and then it forwards that, or it tells the switch to forward the packet to the next node or the next switch, and so on. So the forwarding path is also determined by the switch. And as you can see, the different ports present here. So usually what happens in case of switches or routers is that they have different ports which represent who is connected to who. For example, the port 1 may be connected to one node, and port 2 is connected to another node. So this shows that whenever a message is received through the port 1, and the decision is taken of forwarding it, it can forward it to another node through port 2 or any other port. Now in case of software defined networks, that is not the case. So as you can see here, there are different switches present here, and this is my source, this is my destination, and this is a controller. Now what you see here, open flow switch, what this means is this is actually a switch which follows the SDN, or software defined network standards, instead of traditional network protocol stack. So what does open flow mean? Open flow is actually the most prevalent or the most dominating protocol in terms of software defined networks. So let's go through what happens here. So this is the first thing what happens. The first packet arrives. Usually every first packet misses the entry, because for the first packet the switch does not know where to send it, because it does not have any information regarding any packet yet. So the first packet is missed, that means it is dropped. And what happens is the switch asks the SDN controller what to do. So this is the step 2, the flow forwarded to controller to get action to be taken on particular flow. So now the new term that you can see here is flow, because instead of a route it is now called a flow, because the flow is somewhat different for a route. So for the same data packet the route may be different, which is why it is now called a flow. The flow is usually decided not only based on the shortest path, but also based on, let's say, the path which has the less packet drops, or there's less traffic in that area. So these things, so we'll learn about the advantages of SDN later on. So the second step forwards the query about the first packet received to the SDN controller, and the third step is the controller installs the new flow entry. So this means that the controller has now taken the decision on where to send this packet and how to send this packet, right? So now this controller notifies all the switches in that flow or in that path about this new route or this new path, so that it can forward the packet later on. So once all the switches know about this, then again if the packet is sent, then it is forwarded to the next switch, and so on until it reaches the destination. So in order to convert the traditional protocol stack into the new stack, which is the SDN, there are a few steps that we have to take. For example, if we assume that a traditional network has n intelligent routers or n number of nodes, then in SDN all the intelligent routers are replaced by simple data forwarding switches. So why is it replaced by data forwarding switches? Because now all the intelligent stuff are done by the controller. So the switches can do only what the controller tells them to do, which is why they are much more simpler and can only forward data. So each router will only have one controller. So here by router we mean the SDN switches that we are talking about. So each switch will actually have only one controller. So they will not communicate with any other controller besides its own controller. So this decreases the confusion that might arise if multiple controllers were to control a single switch. So assuming that there will be k controllers, so we already assume that there is a fixed number of controllers in the network. So each switch falls under one controller. So there are k clusters or sub-networks formed. So if you can understand this, if there are n switches and each of those switches falls under k controllers, so that will form k different sub-networks, right? And in each of those sub-network or each of those clusters, there is only one controller which is tasked with the decision making of all the nodes in that cluster. So for inter-cluster activities, for example, if one node in one subnetwork needs to communicate with another node in another subnetwork, then as the switch cannot directly communicate with that switch, or the controller of the switch, it asks to its controller. So the controller needs to communicate with every other controller as well. So for inter-cluster activities, inter-controller communication is required. So this is an example network which is called the ARNet. Okay, the spelling is AARNET, but I don't know the pronunciation, so I just call it ARNet. So this is a network present throughout Australia. So as you can see, these black filled circles are actually the nodes, and the black lines are the links connecting the nodes, and the nodes are actually distributed throughout Australia in different places, for example Cairns, Townsville, Rockhampton, and so on. And there might be two nodes in the same area, so they might be named as Perth 1 and Perth 2 and Adelaide 1 and Adelaide 2 and so on. So in this network there's a total of 19 nodes, okay, and there are various links as well. So we are going to see how we can convert this network into an SDN network or software defined network. So that network is now represented as a graph. Okay, so these are all the names of what we saw, and as you can see, the Adelaide nodes are named as 1 and 2. So in each case where there are multiple nodes in the same area, they are named as let's say the area, the name of the area, and then 1, and the name of the area, and then 2. So what we have to do is we have to divide this into clusters based on the number of controllers. Okay, so in this example I'm assuming that there will be 2 clusters, which means there will be 2 controllers. So I have divided this network into 2 separate clusters. So the green colored nodes here form one cluster, and the blue colored node here forms another cluster. So you might be thinking whether this is unequal division or not, but I have used an algorithm here which divides the network based on the distances. Okay, so you don't have to know the specifics about it, but what you have to know is the conversion of a normal network into SDN network requires the placement of controller. So this is called the controller placement problem, and this is actually an NP hard problem, which means it's impossible to come up with an exact solution, and there's a lot of research going on regarding this and SDN as well. So the circles that we see here, this one 3 and 14, these two are the controllers of each of these clusters. So for example, if let's say node 0 wants to communicate with node 13, 0 asks 3 for the route, okay, and then 3 can notify 0 that okay, you can follow this path, okay, this one, and at the same time it also communicates with 14 as well. So 3 lets 0 and 16 know about the new data that will be coming, and 14 lets 13 know about the new data packet that will be coming. So the data packet is then forwarded from 0, and it goes on following this path until it reaches the destination 13. Okay, so this is how the software defined network works. So why do we need SDN? So this is the big question. Why are we changing the entire protocol stack that we have been used to following into a software defined network? So these are the different reasons. The first one is, as the switches are much more simpler and unintelligent, as they only have to forward data instead of taking decisions, which was the case for intelligent routers. So the switches are now much less costly compared to intelligent routers. So adding switches or removing switches is less problematic because they are much less costly, and they're also easy to configure, replace, remove, and add new switches, because you don't have to configure a lot of things now. They're only simple, right? And all of the configuration is done by the controller. So various vendors provide routers, causing a difficulty in managing a network. So this is the case of a traditional network, because there are various vendors providing different kinds of routers. So all of those routers form a haphazard mixture of a network, right? And configuring all of those network requires manually going there and configuring them, and that is also required to be done by different vendors in the same network. So this is very problematic. But in case of SDN, it is now managed by a controller, so it can be managed remotely from an area instead of going to all the switches and configuring all the switches made by different vendors. And the second motivation is the controller now gets an overall view of the network. In the previous case, the routers needed an overview of the network, right? And slowly, as more requirements came, the routers were slowly turned into more intelligent devices, which is why the routers became more costly. But even now, it cannot actually have an overall view of the network and take difficult decisions, because it has limited processing power, right? And limited memory as well, and it has to also process the incoming packets and send them. So it is very difficult for the router to be more intelligent, because then the entire network needs to be upgraded and so on. But now, as the controller is the only intelligent being, there can be much less in number compared to the nodes, and the controllers can have an overall view of the network, and they can detect anomalies easily by analyzing the network, and they can also make efficient use of network resources, which is very important, because slowly various IoT devices are coming into the network, and due to the huge influx of devices, it is very difficult to increase the bandwidth, because it's already fixed. And what is possible is to manage the existing resources as efficiently as possible. As a result, what might be needed to be done is, considering the network, it requires to be sent, the packet requires to be sent through a path which has less traffic, or which has less packet loss or less environmental disasters even. So considering all these things, a packet can be sent instead of just considering the shortest path. So this can be easily done by the controller because it has a higher processing capacity and has an overall view of the network. And the third is, the network can be configured and managed easily by a network administrator. As I've already said, instead of going to the switches manually or in real time, it can be monitored and configured by the controller, and someone might be sitting in front of the controller. It might be the network administrator. So it is very easy for the network administrator to control the network now, and there might be different controller applications installed in that server or in that controller, which can make it easy to manage the network, or maybe deal with failures, or even maybe change the protocol of the entire network in one go. So as the entire network can now be controlled through a software, this is why specifically the name software defined network came into being. Okay, so these are the limitations and challenges of SDNs. So as the network is divided, placing controllers is NP-hard, as I've already said. So in the divided network, placing controllers needs to consider various constraints, for example energy constraints, and also cost effectiveness, because now controllers are very costly compared to the switches. So when we're placing controllers, we have to consider the minimum number of controllers that is required to place so that it can deal with failures, and also it can effectively handle the network, and so on. So there are various constraints now, and considering all those constraints, placing a controllers is NP-hard. And also the network is already filled with traditional switches and routers, and the entire network throughout the world is not possible that it will be changed overnight, which is another problem or challenge. So the solution to that is creating architectures which can handle a mixed network. For example, it might have software defined network in one area, or switches and controllers in one area, and it might have intelligent routers in another area. For example, data centers of Google and various other companies now use SDNs, and the regular networks already have traditional network installed, right? So creating an architecture or algorithm which can handle both of them together is also difficult, because the routing protocols change for a packet whenever it reaches traditional network, and again it changes whenever it reaches a software defined network. And the initial protocol architecture of SDN included only one controller, which created a single point failure, because now the entire network is controlled by one controller. So if that is somehow jeopardized, then the entire network is actually in problem, because the network cannot take any decision without the controller. So various other security issues also came into being, which was solved by a proposal of multiple controllers. But now, as I've already said, due to the presence of multiple controllers, placing controllers became NP-hard, and it still has some security issues, because you have to deal with attacks which can now be centralized. So now, instead of attacking a switch or a link, everyone can attack a controller. Although this is difficult because the controller has much more processing power, but it is still an issue. So these are all the limitations and challenges of software defined networks. Okay, so at the end of this slide, I'm going to say a few things, because this is the end of the different types of network overviews that we have learned throughout the course. So this is the last lecture where we will be only learning a brief overview. So from the next slides, or from the next lecture, we'll be learning in details about different protocols and so on. So the things that I have said about all the networks, I have mentioned in most of the cases I've mentioned the challenges and the different limitations of those networks. Those actually indicate fields of research. That means there's research still going on with those areas. And as I've already said, the next topic will be regarding the existing stable networks. So what I've seen throughout the previous lectures are the networks which are still being developed for different scenarios. But later on what we'll be seeing is regarding some fixed networks which already have a stable configuration and documentation. So we'll learn about them more. So the next topics will be more understanding than knowledge, and we'll dive deeper into the specific networks. Okay, so this is the end of this lecture, and actually end of a part of this course, which is learning about different kinds of networks. So if you have any question, feel free to ask. And with this I'm going to end today's lecture, I guess. Assalamu alaikum everyone.